When you send a large file across a network, it is not sent as one continuous stream. It is broken into small, equally sized chunks called packets, and each one is sent separately. That sounds like extra work, so it is worth understanding why it is done. If a single large message traveled as one block, it would occupy an entire route for as long as it took to get there, and everything else would wait. Worse, if any part of it were corrupted, the whole thing would have to be sent again. Breaking it up solves both problems. Many messages can share the same links by interleaving their packets, and if one packet is damaged, only that packet is resent, not the entire file. Every packet has 3 parts, and the syllabus expects you to know what goes in each. The header carries the addressing and control information, the sender's IP address, the receiver's IP address, the sequence number of this packet, and the total number of packets in the message. The payload is the actual data, typically around 64 kilobytes, and usually described as the body of the packet. The trailer marks the end of the packet and carries an error checking value, commonly a cyclic redundancy check. Of those fields, the one to pay attention to is the sequence number, because in a moment you will see exactly why it has to be there. Now the switching itself. The message is split into packets, and each packet is passed to a router. The router examines the destination address and decides which link to forward it along, based on how busy each route is and how many hops it would take. And here is the crucial part. That decision is made independently for every single packet. Packet 1 might go one way, packet 2 another, because conditions changed in the fraction of a second between them. Nobody plans a route for the message as a whole. There is no fixed path reserved from end to end, which is precisely what distinguishes packet switching from the older circuit switching used by traditional telephone systems. So let us send 4 packets and follow them. They leave the sender in order 1, 2, 3, 4. But they are traveling different routes, and those routes are not equally fast. One has fewer hops, another is congested. Watch what happens as they cross. Packet 3 took the shortest route and arrives first. Then packet 1. Then packet 4, which went a long way round, and finally packet 2, which hit congestion. Look at that arrival order, 3, 1, 4, 2. The packets arrived in a completely different order from the one they were sent in, and this is normal. It is not a fault or an error. Now the sequence number in each header does its job. The receiver reads them, sorts the packets back into 1, 2, 3, 4, and reassembles the original message intact. Without that number, the receiver would have a pile of data and no way to know how it fits together. So what are the benefits? There is no need to reserve a route in advance, so the network is used efficiently and many transmissions share the same links. If one route fails or becomes congested, packets are simply sent around the problem. The network reroutes automatically without the transmission failing. It is resilient by design, which is exactly why the internet works this way. And because packets are small and independently checked, a corrupted packet means resending a small chunk rather than an entire file. Efficiency, resilience, and cheap recovery from errors, all from the same design decision. It is worth seeing what packet switching replaced, because the contrast makes its advantages obvious. The older approach is circuit switching, used by traditional telephone networks. Before any data moves, a complete path is reserved from sender to receiver, and it stays reserved for the entire duration of the connection, whether or not anything is being sent along it. That guarantees a steady, predictable connection with no reordering and no congestion, which is exactly what a voice call wants. But it is wasteful. During every pause in a conversation, the whole circuit sits idle and unavailable to anyone else. And if any link on that reserved path fails, the connection drops entirely because there is no alternative route. Packet switching gives up the guarantee in exchange for sharing the network efficiently and routing around failures. That is the trade, and a question asking you to compare the two is really asking you to state it. The drawbacks follow from the same design. Packets arriving out of order have to be reordered before anything can be done with them, which takes time and memory at the receiving end. Packets can be lost entirely and have to be requested again. And every packet carries a header, which is overhead, data that is not your message but is needed to deliver it. So the total transmitted is always more than the file itself. That reordering delay is why packet switching is less suited to real-time applications like live video calls, where a late packet is worse than a missing one, and why those applications need extra protocols on top to cope. 3 things to take away. First, if you are asked what a packet contains, give the 3 parts by name: header, payload, trailer, and put the right things in each. The commonest error is putting the sequence number in the payload. It is in the header because the routing and reassembly machinery needs it without opening the data. Second, if you are asked why packets may arrive out of order, the answer is that each packet is routed independently and different routes take different times. Saying the network is busy is too vague. Third, if asked how the message is put back together, name the sequence number specifically and say the receiver uses it to reorder the packets. That single term is what the mark is for.